In this representation, the sign digit is 0 for a positive number or 9 for a negative number, right? So they're suggesting maybe adding the 10's complement to the 2's complement. So maybe we should just figure out manually a few of these examples. So if we want to subtract 3 from 9, so in 10's complement, this would be the same as adding 9 plus 97, if you like. Right? I think that's right. 0 is 9, 1 is 8, 2 is 7, no, 96. So 6 and 9 is 15. Well, that doesn't look right, does it? Because we should have 6 as the result. And that doesn't look like 10's complement, that looks like 9's complement. I think we need to add 1 to that, don't we? To make it a 10's complement. There's my rubber. So this should really be plus 97. In which case you're going to get 16, which is the right result, given that we dropped the 1 off. We don't care about that output, right? But they're suggesting doing, it's a binary version, so BCD operands. So in BCD, this would be something like 1001 plus, well, 7, which is going to be 111, right? 0. So we've got 0, 0, 0. That doesn't look right. Anyway, 1, 0, 0, 0, 1. That doesn't look right, does it? Why is that wrong? So 9 plus 7, 16. Yeah. 10, 9, that's correct. Don't exactly know why I'm going wrong there. Can anybody see what I'm doing wrong?
Is it not 0, 1, 0, 0 is the 3 complement?
I'm not too sure yet where that's going wrong. So, well, I know why it's going wrong, and it's for the same reason that you have in the lab. You've got to correct this. So this is binary, not BCD. This is 16, so in BCD, this should really be 0, 1, 1, 0 plus 1, right? So that's where the error is. But as for a good approach on how to do this, I think first you've got to be able to, well, to derive the 10's complement is easy enough, and I think that is in the lab, isn't it? So if you have the BCD digit 0, 1, 2, 3, 4, 5, 6, 7, 9, then it's 10's complement is going to be 9 plus 1, which is going to be 10. I don't know how to represent that really realistically. So if it's a single digit, it's going to be 0 as well, right? 1 is 8 plus 1 is 9. 8, 7, 6, 5, 4, 3, 2, 1, right? And the binary for those, of course, and so on. This is going to be 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, and so on. So the problem is when this goes over over 9, we have to compensate for it, right? Because we had to rewrite 16 as 1, 0, 1, 1, 0. So 9 goes to 1, 0, 0, 1, which is fine. 10 should go to, well, that's going to be 9 plus 1, so that should be 0, 0, 0, 1. Maybe I should make this a more significant bit as well. So this goes to 0, 0, 0, 0 plus. So this is in the more significant, this is BCD 1, if you like. And BCD 0 should be 1. 10 will be 0, 0, 0, 1 with 0, 0, 0, 0. 11 will be 12. So we've got to worry about 13, 14, 15, 16. Do we have to worry about anything above 16? Right. I think I'll take this offline and I'll come back to you next week on this problem because this is going to take a while for me to figure out myself. I don't really know. I haven't prepared the question. So come up with something that is easier to solve. I mean, clearly what we need to do is figure out what the representation of the sums are on a digit by digit basis. So at the most we could get 18, right, as a result, because at most we're going to be adding 9 and 9 together, and therefore we have to figure out, well, what each of these correspond to. 18 is going to be a 1 plus an 8, obviously. Sorry, that's 8. And we want 7 for 17, right? And so on. So, when we're adding two BCD or subtracting two BCD digits, what we're going to be doing is adding the tens complement of a second BCD digit. And what we might do is get a digit out plus a carry of 1, right? Which is going to be this. But we have to figure out, instead of course, when the sum is 10 or greater, we have to convert the result. So instead of it being 1, 0, 1, 0, the result should be 0, 0, 0, 1 and 0, 0, 0, 0, right? And this is exactly what you've got to figure out in the lab as well, I'm pretty sure. Right? You've got to figure out, well, how do you compensate for the fact that we're representing the result as a BCD answer. Right, so there's two issues. Firstly, we need to convert to 10's complement. Then we need to add, and there may be a correction involved. Okay? Is that all clear? So, and we've got to do that effectively in every digit position. So, of course, the same calculation can be done. Remember that the 10's complement is really just going to be the 9's complement with 1 added to it, whereby you need to do this compensation as well. If you already have 9 in a digit and you add 1 to it, well, that has to become a 0 with a 1 carry, right? So, but I'd worry about that as being the carry in. So if we have some block of logic and we have 2 BCD digits coming in, we have a carry in as well and a carry out. And of course the sum, BCD sum. So that's what we want to have. So what are the possibilities here? I mean, this is precisely what's in the lab. Are you already doing this? This is lab 3, right? It is lab 3, I think. Is it lab 2, is it?
Yeah.
Oh, okay. Right, lab 2. What's lab 3 about then? That's flip-flops, is it? Okay, fine. Good. So, you know the solution to that. What is it? You tell me. Sorry? Could you speak up? I can't hear you. That's a bit vague. I don't really know what you're talking about. Can you be a bit more concrete? How do we add 2 BCD digits together? This is something you're doing in the lab, so how have you done it? I know you've done it, for example.
For full adder.
Say again?
Ripple add, full adder. Chain it. The adding part.
I'm not clear on what you're saying. So here we've got a 4-bit circuit. We're adding 4 bits together at a time in our circuit. Yes?
So you just sort of treat it as normal addition up until it overflows, and then you use the carry out to sort of know what wraparounds and then display, I guess, be able to translate it back into higher bit or higher number, sorry.
Right.
I'm thinking about like displaying on the hex though, because if we're outputting a full bit BCD sum, then
Well, it'll always be between 0 and 9, that BCD sum, right? Because your circuit has to correct for the fact that if it's more than 9, what should it be? Subtract 10, yes, effectively. Right. So what's the best way of figuring out what the logic should be in here? Is the specification clear? We're adding together two BCD digits. We know that a BCD digit can only exist between 0 and 9. And we want a BCD sum and a carry out. So if the sum is 9 or less, we don't have to worry, then it's fine. But if the sum is 10 or more, we have to do a conversion, right? So we only have to worry about these results here. So effectively, 1010 has to be converted to 0, and we have a carry out of 1. This is our carry out bit here. 1011, so 11, has to be converted to 1 with a carry out of 1. Now, we can't, there are some sums here that we can't even represent. We're going to be forced into a situation where if we have 15's fine, that could be represented. That, of course, will be converted to 1 and 5, right? But 16 has to be converted, well, 16 isn't a BCD sum, well, it's not a sum that we can even represent. We know we've already got a carry out, so I guess once we get a carry out, which is indicated by the fact that we have at least 16, the 0000 that we have left over has to be converted to a 6, right? So 16 gets converted to a 1 and a 6. All right? So 11 gets converted to a 1 and a 1. And that would be the same, actually, as adding 6 to 11, would it not? The binary result would be the same as adding 6 to that result. Because if we took 11 and added 6 to it, then we're going to get our 1 and our 1 result. And it's the same for down here. If we've got 16 and we add 6 to that, well, then we're left with 6 over here, right? This is our 16 line. 17, which would be represented as a 1 and a 0001, if we added 6 to it, would become a 1 and a 7. Here's our 7. So it seems like if we've got 10 or more as a result, then what we want to do is add 6 to it. So that's what the addition part is doing. How do we know we've got 10 or more as the result? Yeah.
You can do the circuit where like there's a 1 in the leftmost bit and there's a 1 in either the second or third position, then there is definitely about 10.
Mm-hmm. Yep. how does that solve this case?
Oh, so you have to put another or for if it's greater than, if it's a,
So I think you have to check you've got a carry and or you've got 10 or more in your sum, right? And in that case, we just want to add another 6. And the result should be fine. Okay? So that's the addition part. And it looks after the correction part as well, right? Because we've figured out how to do that. What we haven't yet effectively done is converted our addend to, or our subtrahend to a tens complement number in order to perform this addition. So how do we do that? Right, it's the same as forming the nines complement, so subtracting every digit from 9 and then adding 1 to the result, whereby that 1 is going to be a carry in to the least significant bit. Does that make sense? Just like it was for our binary add subtractor. So where does that put us? So to convert to tens complement, just form the nines complement of each digit. And add 1 into the carry in of the least significant bit. Does that make sense? You're the one that asked the question. Do you understand this bit so far? And then at each bit position, at each digit position, we're going to use this circuit where we still haven't really defined what that's doing, but it's just a 4-bit binary adder of some form or another, right? Doesn't really matter what it is. And then we have to check the result. So to use a 4-bit binary adder, so this is specifically for BCD subtraction, at each digit to form a, well, I'm going to call it an initial carry out and sum, right? And we're going to check, oh, sorry, let's just make this slightly different. I'm going to make this 2A. And 2B. If initial carry out or sum is greater than 9, then what we want to do is add to the initial sum, right? Or to form the final, to form the BCD sum. Right? Do we need to worry about carry out? We do. We also need to ensure that we set the carry out, the BCD carry out, to 1. Otherwise, else the BCD sum is the same as the initial sum, and the BCD carry out is 0. Right? So that's what we want our circuit to do. Can you all read that? Is that clear? Any questions? Right. Right. Is this enough? Do we need to worry about the circuit design? Or are you guys right with that? Sorry? You should be fine. Okay, good. So you know it's just a 4-bit adder. Okay, good. Great. How do you do the addition of 6 to the initial sum? Any ideas on what to do? What happens if we just use a second adder and add 6 to the result? Is that cool or not? Why? Yeah, we don't care about we're not going to worry about the one that comes out of that second addition of 6. That's true. Because we're going to set that anyway, the BCD carry out to 1, just to make sure. We've now got 2 adders there, and it's going to take twice as long. Is that desirable? Can we do better? What could we do? So we're worrying about 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1, and we're also worried about 1 0 0 0. That's 16, 17, 18. And that's the maximum that we can get because we've got 9 plus 9 is 18 at most. Now this has to become So 10 has to become 6, right? That has to become, well, 1 and 0, 1, 1, 0. No, I'm wrong. Not that. It has to become 1 and 0, 0, 0. So this becomes 1 and 0, 0, 0, 1. Um, 0, 1, 0, 0. 15, yep. 0, 16. 17. And 18. Right, so this is our initial sum. And this is the BCD sum that we want to display, right? Well, that's the result, really. So let's call this I3, I2, I1, I0, and this is B3, B2, B1, B0. What's the relationship between B0 and I0? So B0 is equal to I0, right? What about B1? B1 looks like it's the complement of I1. Is that right? What about B2? So that's 1 here. So that's 1 when we have those two, and 1 when we have these two. So it's the exclusive NOR of I2 and I1. Would you agree? By the look of it? Because it's 0 in every other case where those two bits are exclusive OR, are true when they're exclusive OR. And what about B3? Looks like it's not I3 and I1, is that right? I might not have been a good choice for it. But does that look right?
Could you OR I3 with, what is it, B1, then just reduce B1 and say, like, not I3 or not I1? Because B1 is not I1.
So that's not I3 and not I1.
Oh, no, I didn't see the 1 at the top of B1.
Sorry?
Oh, I didn't see the 1 at the top of B1. So I thought you could just OR B1 and
I know it's not really neat what I've drawn up, but so you're suggesting a simplification of this, are you?
I was, but I didn't notice the 1 at the top of B1, so I thought you could OR B1 and I3 because, and then...
B1 and I3. Ah, yeah, these two.
Because it would just set the bottommost bit to 1 if you then invert that. Then,
Right,
yeah. It's probably not simple.
okay. So, clearly that's better than having another adder, because you've got 4 equations and there's literally only one inverter, two inverters, one AND gate, well, and a slightly more complex gate, the exclusive NOR gate, that are required altogether instead of 4 full adders, because you're only adding 6, it's a very specific number. That's always going to be a lot cheaper than having a general purpose solution like a full adder or a full 4-bit adder to do your addition for you. Okay? The nice thing about FPGAs is you can specialize the circuit and thereby have a much cheaper circuit to be implemented. So, depending upon the application, FPGAs are used in a lot of filtering applications, a lot of signal processing. So we generally have to use then the coefficients of our filters as constants within our circuits and multiply those constants with whatever value has been received on an antenna in order to do the filtering on that. And it's much cheaper generally to use a specific adder or a specific multiplier than it is to use a general purpose one. And that gives us great advantage in the FPGA. What's more, we can reconfigure the FPGA as those constants change. But in any case, so to do 2B, we only have to implement this circuitry here, right? This is only going to be coming into use if the initial carryout or the initial sum is greater than 9, right? So greater than 9 means that we have I3 and I2 or I1, as was previously pointed out. Okay? So I hope that this is clear what you need to put in there. And I'm pretty sure this has now given you a pretty good leg up as far as that second lab is concerned. Does this help with lab 2? It does. That wasn't my intention to help you. Sorry? You did it a different way. Okay.
Well, I got the same result.
Good. What way did you do it?
Well, I just completely disregarded I3.
You completely disregarded what?
I3.
I3.
Yes, because above that, that value, you can just go your carry out bit.
Hmm?
You can just put your carry out bit in, and then work it out with the carry out bit, and then release through I2, I1.
Oh, you mean you're using this bit
And zeros.
and these 3 bits?
No, yeah.
But you still have to worry about 10, don't you? And 11 and converting those. Do you not? It's a while since I did this lab, several years ago, so I can't really remember precisely what was required.
The first two are 10 and 11, right? Up there.
Yes.
So even if you get rid of I3, it doesn't matter. You still work out 10 if you use the carry out.
But if you're ignoring I3, how do you distinguish between 10 and 2?
Because when, sorry, 10 and 2.
In the lab, it's a different truth table. So like the
Is it?
the S3 was just like zeros for the bottom half and then 1 for the top half.
Okay.
And then removing it still keeps everything distinct.
All right. I believe I cannot picture the lab in my mind. I remember you had to do something about BCD addition. In fact, I thought you had to go and do subtraction as well. But okay, are there any other questions that hopefully can take up the last part of this hour? I would not have thought that this would take so long. Any questions? Right. So we're going to go on to the lecture then? There's no questions? All right. Very good. How many of you are getting around to having a look at the exercises? Only 2, 3, 4? I think it might be worthwhile. Like, there is this ongoing suggestion it is recommended that you practice solving more problems of this style to prepare for the quiz, right? So I think the main problem that one faces in this course is not so much figuring out how to do it correctly or not, but it's also being quick enough and being familiar enough with the techniques to figure stuff out quickly. All right? So you get that through practice. The more practice you do, the more smooth your understanding and your ability to put into practice the techniques that we've discussed in lectures become. You don't have to think about, well, what's the complement and how do I derive the complement? That should be like second nature or become like second nature to you. Being able to potentially read off from the truth table what the equations are, rather than relying on a Carnot map, which of course is going to take a lot longer to build up. You still might have to justify how you obtained this, but that might still be quicker than drawing up a Carnot map. Okay, good. So let's get to the lecture then. Right. Turn down the lights a bit. Okay, recall that we were talking about flip-flops, registers, and counters, and we started this lecture on Tuesday. We talked about several of the topics that are relevant in this chapter. We did not talk about the 2 points that are grayed out here. Now I'm going to do a very quick review on latches and positive and negative edge-triggered flip-flops before we'll go on to consider timing properties of flip-flops, how to build counters, and how one does timing analysis of flip-flop based circuits. So we looked at the gated D latch on Tuesday. This was sort of the first memory element that's in common use that we looked at. Has the S and the R inputs of an SR latch tied together via an inverter, so that the legal input of S and R both being 1 or both being 0 in the case of the SR latch is not encountered, right? The way this guy works is as depicted down here in this timing diagram. It's fairly straightforward. When the clock goes high, that enables these 2 NAND gates and therefore allows not D to be presented over on this wire here and D on this wire, and conversely not D to appear over on the output side and D to appear on the output side for the Q input. So when the clock is high, we see whatever is on the D input being reflected in the output of the latch, and whatever the value of D is when the clock goes low again, that is what's stored in the latch until the clock goes high again, in which case the D input again is what is reflected on the output of the latch. So we say that the latch is transparent for the period that the clock is high, because we see whatever is on the D input is reflected on the output. But you could also sort of say that the active edge for the D latch has two active edges on the clock. It has the rising edge and the falling edge, because both of those are significant. At a rising edge, we could get a change in the output, and on the falling edge, the output is frozen. We're not going to get any further change in the output from that period on until the clock goes high again. We then used two of these D-type latches, so exactly the circuit that we just saw, wired together in this way, in this manner, where we invert the clock on the slave latch with respect to the master latch. And that gives us very specific behavior. We note with this design that when the clock is high, the transparency of this latch allows QM to vary as D does. So that's in this period, for example. We see when D goes high while the clock's high, QM goes high, right? Because the clock on the other slave is low, we get no output in no change in QS during that period. However, when the clock goes low, that is when the value on QM becomes frozen. So this value becomes frozen until that time that the clock goes high again. And during this period, while the clock is low, the slave latch becomes active because the clock is inverted and it sees a high clock now. And that means that whatever is on the QM signal is now transferred to the QS output, the output of the slave latch. And because QM can't change over time while the clock is low, QS only ever sees one transition. It sees that transition at the moment that the clock goes low and the slave latch becomes active. That's when we see a transition in the output QS here. That's what also happens in this second period when we see the clock's active here or high, D is low, and therefore QM goes low. And so when the clock goes low and the slave latch becomes active, we see QS going low. Okay, so in effect, QM can change its state whenever the clock is high. QS, of course, will only change state when the clock goes low, and it'll only change it at that point in time because QM, the input to this latch, is frozen for the period that the clock is low. And so we actually have the input D being stored to QS only on those edges where the clock is going low. So we call this a negative edge-triggered D-type flip-flop. And that's illustrated by the fact that we have a notch there to indicate that it's edge-triggered and the bubble to indicate that it's negative edge-triggered. We also looked at a positive edge-triggered D-type flip-flop, which conceptually is a more complex looking circuit, but it saves on hardware and is therefore desirable. Of course, the negative edge-triggered flip-flop has a comparable 6 NAND gate design as well. It isn't usually implemented using master-slave latches. In this particular case, when the clock is low, because these inputs to NAND gates 2 and 3 are low, P1 and P2, those two wires, are going to be at 1. And as a consequence, we have that feedback loop operating here on the output stage, or the slave, if you like, of the positive edge-triggered flip-flop. Q will be reinforced by this NAND gate, or rather, Q is reinforced by the fact that you have Q bar coming into NAND gate 5 with the other input being 1. With one of the inputs being 1 on a NAND gate, the other input is inverted. So the Q bar becomes a Q, and we get this reinforcement occurring on this feedback loop at the back end. Interesting things happen when the clock goes high here. When the clock goes high on these two NAND gates, we see that the not D input, well, we previously had not D on P4 because P2 was at 1 and therefore it inverted the D input. So we had not D on this wire. together with now a 1 coming in, and, well, this guy is either 1 or it becomes not D because there's a D at point P3. So we either have 2 1s and a not D or 2 not Ds and a 1. In either case, P2 is going to go to D. And by a similar argument, P1 is going to go to D bar. Which one's low, which one's high, doesn't really matter. Without loss of generality, one of them is going to be low, right? Let's say it's P2, that D is low, right? In that case, Q is going to go to 1. Sorry, Q bar is going to go to 1, right? Because it has a 0 input here. So that means Q bar is going to go to 1. And since D is 0, D bar must be 1. So the 1 and the 1 together here in this NAND produce a 0 out. And therefore, we're going to get D on the output side there at Q, right? Now, if D is 0, when the clock goes high, P2 is going to go to 0. And as a consequence of P2 going to 0, this NAND gate here is going to be forced to output a 1. Irrespective of what D does, this guy is going to stay at 1. So we're isolating the flip-flop from any further changes in D once the clock goes to 1. Is that clear? When the clock goes to 1, this guy goes to 0, assuming D is 0. And because it goes to 0, the 0 into this NAND gate forces this NAND gate to have a 1 out. Doesn't matter whether D is 0 or 1 after that instant. Once this guy becomes 0, P4 is always going to be 1. And as a consequence, any further changes in D aren't seen on the output side of this flip-flop. Is that clear? Similarly, if D happens to be 1 when the clock goes high, then this point, P1, this Y, is going to go to 0. And if it goes to 0, that forces this NAND gate here to output a 1. It'll also force this NAND gate to output a 1. And there aren't therefore any other possible changes once, if this guy goes to 0, P3 and P2 go to 1, and as a consequence, again, there's no further change in, or no change in D. Anything that happens in D can no longer be seen by the output stage of the flip-flop. So what that means is, after the clock's gone to 1, any further changes in D aren't seen by the output. So it's only triggered on that positive edge. There's no more transparency to the D input here. I hope that's clear. I hope when you look over it again at home, you'll see this, okay? So, looking at these 3 devices, we have the D-type latch, which has just got clock labeled here. We have a positive edge-triggered D-type flip-flop, which has a notch there, and we have a negative edge-triggered D-type flip-flop at the bottom. And the response of those to the input curve of D here with that clock signal is that the latch, QA, is going to be transparent while the clock's high. So we see the changes in D while the clock is high. And while the clock is low, so when it freezes for the period the clock is low. Since D was low at that point in time, it stays low. Since D is high at this point in time, it stays high. Okay? No further changes possible. As for the positive edge-triggered flip-flop, it only changes on positive edges of the clock. So when the edge changes from 0 to 1, D is high, therefore QB goes high. Here again, we have a positive edge. D happens to be low, therefore QB goes low. And as for the negative edge-triggered flip-flop, it's only concerned with the negative going edges of the clock, which initially coincides with D being low, therefore there's no change in QC, whereas at this point in time over here, D is high, so QC goes high. All good? Good-o. Right, so let's talk about timing parameters. So there's 3 timing parameters that are important as far as flip-flops are concerned. So-called clock-to-Q propagation delay, TCQ, which is the time period that signals need to emerge on the output side of the flip-flop after a clock goes high or after the triggering clock edge. If it's a positive edge triggered flip-flop, it's after the clock goes high. Negative edge triggered flip-flop, it's after the clock goes low. So it's the time between that instant occurring and the output changing as a consequence of that. Okay? I'll define these first and then show you a little bit more about them in the subsequent slides. The next timing parameter is the so-called setup time. Unless you hold the input D constant for a period of time around the triggering edge, that input isn't necessarily reliably seen by the output of the flip-flop. And therefore, we need to ensure that this minimum period of time, the setup time, is observed. Otherwise, we don't get a reliable transition in the flip-flop. Finally, there's the so-called hold time. This is the amount of time that you need to keep the input D constant after the triggering edge. If you don't do that, again, the flip-flop may fail to change state. These parameters vary for different process technologies, different architectures, and different voltages that you're operating the circuits at. But I'll show you what is considered normal. So, just looking at a D-type flip-flop, as illustrated here, we have here a positive edge-triggered flip-flop. So we see on the rising edge of the clock, D is high at this point in time, but there is a delay before the output actually goes high. And that's because the gates inside the flip-flop have latency associated with them. They've got a capacitive load, there are resistances that restrict how quickly you can charge or discharge the transistors inside those gates. Okay, and that contributes to a latency in the output going high. Again, over here we see a rising edge, D being low. Again, there's a delay before the output goes low. And this TCQ propagation delay might vary, going from 0 to 1 and from 1 to 0. So they're usually specified with min and max values, as we'll see. Let's see how this TCQ comes about, the clock-to-Q propagation delay with the gated latch. It's the simplest circuit, so I think it's easier to appreciate with this device than it is with the flip-flops that we've looked at. So all we need to do is make an assumption about the latency or the delay, the propagation delay of a gate. That's usually called TPD, the propagation delay. And we're just going to assume that the delay of all gates is the same and it's delta nanoseconds. So it's small, but it's measurable. It's not true that all gates have the same propagation delay either. The larger the gate, often it's a smaller delay because there's higher power involved. But if you have more inputs or more load on the gate, that's going to take longer to charge and discharge that gate, so that propagation delay can increase. Generally, an inverter is going to have a smaller propagation delay than an AND gate, but we're just going to assume, for simplicity's sake, that all gates have the same propagation delay. We are also going to make the assumption that unless a signal is presented to the input of a gate for at least delta period of time, then that gate isn't going to change state. It never even sees the input. And that's because there's not enough charge that's been presented to the gate if the signal's only present for a very short period of time, there's not enough charge to charge up the gate. And as a consequence, the gate won't even change state. So let's just make those assumptions. And have a think about, well, what happens when D changes here in this latch? Or rather, I think when the clock goes high. So let's assume the clock goes high at time 0. If that's the case, then at time delta, after time 0, this NAND gate is going to change from 1 to 0 because the D input is high. We're going to have 2 1s coming into this NAND, therefore it must go to low. And as a consequence of this change in state, the output of this second NAND gate up here is going to change from 0 to 1 after 2 delta. And similarly, after 3 delta, this lower NAND gate is going to change state, because if this guy's gone to 1 and this guy stays at 1, the output of this NAND gate has to go to 0. But as you can see, there's a 2 delta delay before Q changes and a 3 delta delay before Q bar changes. Okay? And so on a 0 to 1 transition in the output, we can see that there'd be a 2 delta delay. But if we were changing from 1 to 0, as is illustrated in this second example here, the roles of Q and Q bar are going to be flipped around, and as a consequence, we'll see that there'll be a 3 delta delay before Q changes, because the delay has to come via a change in Q bar before Q can change. So the punchline really is that the clock to Q propagation delay is smaller here for 0 to 1 transitions than it is for 1 to 0 transitions. All right, let's have a look at this setup and hold time. Yes, sorry.
Why is 2 delta for 0 to 1 transitions?
Why is it 2 delta for 0 to 1 transitions? Because we showed here that Q changes from 0 to 1 at time 2 delta. If D is 1 and Q is initially 0 when the clock is 0 and the clock goes high, it's going to take 2 delta time before Q goes to 1.
Why we don't care the 3 delta Q?
Because we're concerned about, it's the clock to Q propagation delay that we care about, not the clock to Q bar. So the output of the flip-flop is taken as the Q output, not the Q bar output. All right? Okay. So we've talked about the clock to Q propagation delay. Now I want to focus a little bit more on the setup time and hold time. Here, with respect to a D-type flip-flop, we're going to look at what happens when the clock goes low on that gated D latch. So when the clock goes low, there's a period of time prior to the clock going low whereby the signal has to remain constant, otherwise it will not be seen on the output side of the latch. So here we see that D goes high well ahead of the clock going low, and therefore this setup time, which is this narrow period prior to the clock going low, is satisfied as much, we've given it much more time. However, if this D had gone high somewhere inside this period, then that would mean that we may not see the D going high on the output side of that latch, or not see it reliably. It might go metastable, as we'll see in a moment. There's also the concept of hold time, which is the period of time after the clock going low that the D input has to be held high. Otherwise, there's a chance that we're going to misread the data input that we had just prior to the clock going low. If we hold it constant for more time than T hold, that's fine, but the critical period is if D changes somewhere between the clock going low and this minimum T hold time. If D were to go low somewhere before that, it's possible that we would not reliably have read D then in the output side of our circuit. So let's have a look at this first from the perspective of the setup time. Let's have a look at this circuit first. Here we have the clock is high, and we have D changing from 1 to 0 at time 0, let's say. Then the configuration of the circuit implies that the R wire is going to change from 0 to 1 at delta time due to the delay of the inverter. And we're also going to have the output of this NAND gate up the top here changing from 0 to 1 at delta time because D has gone from 1 to 0. Okay. As a consequence of this guy going to 1, the output of this NAND gate is forced to 1 at 2 delta time, but it's already at 1, so we don't really even see that change. But what we also see as a consequence of the R wire going to 1, with the clock being 1, that the output of this NAND gate has to go to 0 at 2 delta time. Okay? And as a consequence of this wire going to 0, this NAND gate has to go to 1 at 3 delta time. Okay? And together with the 1 that we see on this wire now, we will see that the output of this NAND gate goes to 0 at 4 delta time. All good? All right. So we have to wait effectively 4 delta time for the output to even go to the right value here after the data signal changed. And unless the clock waits for at least 3 delta, a period of 3 delta after D changes, we're not going to reliably see the output. Let me show you how. So if the clock were to change from 1 to 0 at 3 delta time, then that would imply that this wire here is going to go back to 1 at 4 delta time, because now we have a 0 on input. After 3 delta, we get a 0 input on this NAND gate. As a consequence, this NAND gate has to go to 1 at 4 delta time, right? But at 4 delta time, well, that's the time that this guy has just gone to 0. So now we have the 0 coming in here and the 1 coming in here, and therefore the output here is going to go to 1. So that's fine, because that's exactly what we desire, right? But what if the clock changed just before 3 delta? Well, then this wire would go to 1 before this guy's even gone to 0. And as a consequence, this guy could go to 0 again. So that would mean that we don't reliably latch in the feedback loop here the input, because there's a time difference between when Q and Q bar become the final value, the desired value, and we have to wait for that value to be reinforced by the gates so that we know it's stable. If we don't wait that period of time, we could very well enter a period of metastability on the output side of this latch. And that's why we have to preserve this setup time. We have to be sure that we've given our device, our flip-flop, our latch, enough time to see the input at the outputs. Okay? Now, I'm not going to expect you to be able to explain the phenomena I've just talked about, but I do want you to appreciate how it comes about. So I'm hoping you understand the explanation. So for 20 28 nanometer CMOS devices, typical values for the setup time and the hold time are sort of, as stated here, maybe up to 0.1 nanosecond, 0.05 nanoseconds. But for the 28 nanometer RTX7 FPGAs that you're using, they already have pre-built latches, and they're configurable latches. They can be configured for lots of other things as well. So they're a little bit more general, and therefore the setup time and hold time and the propagation delay are considerably higher than the normal 28 nanometer sort of parameters that one would talk about in VLSI circuits. So this is just to give you an idea of how large these numbers are for the device that you're actually using. So it can take up to half a nanosecond for the output to be correct. So that means, you know, if you're operating the device at faster than what, 200 megahertz, you might not even see output changes before it actually gets a new input and therefore has to change the output again, right? Because it's taking half a nanosecond here for that change to occur. All right. I can see that this argumentation is probably not being well understood. Who would say that they understand what I've just been talking about? You're not just saying that out of bravado, are you? Okay, so you have some sense of what I'm talking about. This is the last sort of conceptually complex slide that I have for today, I think. Well, there might be another one that'll throw you right at the very end, but don't worry too much about it. And this one here is really just to illustrate how the hold time could be important, but hold time's really even harder to justify or to qualitatively explain than setup time. Here we make the assumption with our positive edge trigger D-type flip-flop that the clock goes to 1 at some instant in time, and we know that that means we're going to get changes in P1 and P2 in response to what the data input is. Now, if D is 0, we know this point has to go to 0, right? But it's not going to do that instantly. It's not going to do it at the very instant that the clock goes high. Rather, there's a latency that's associated with this NAND gate as to how long that's going to take, right? So there's, let's say, a delta delay before P2 goes to 0. But what if D changes between 0 and delta time? Well, that means that this guy could therefore change because this guy isn't at 0 yet. And as a consequence of not being at 0, the 1 is still active, and therefore whatever D changes to, we're going to get not D occurring over here on P4. And so that breaks the assumptions that we made about this positive edge triggered flip-flop, that P2 is always at 0 before we get any change in D. If that is the case, fine. We're going to be insulated from any changes in D. But if P2 takes some time to go to 0, and in particular, this 3-input NAND gate is going to be slower than this 2-input NAND gate, and therefore it's going to take longer for this guy to get to 0 than it takes this guy to invert D to D bar. And as a consequence, we could have a failure of the flip-flop to accurately trigger based on the value of D. All right, so that's really why we need to also be concerned about how much time after a clock edge we hold the input constant for. We have to ensure that it's held constant for a period that allows the input to be seen at the output of the flip-flop. Okay? That's it. Are there any questions about this? As I say, I'm not expecting you to reproduce the analysis. I'm expecting you to understand how these phenomena come about. That's all. All right. No questions then? Okay, so let's continue. So we're going to shift gears to somewhat easier material, given that it's 20 past 2, it might be a good time to have a 5-minute break, and we'll resume when those 5 minutes are up. Okay? Are there any questions?
I assume we might simplify that into like a box or
It could be a mux, couldn't it? Yeah. It's usually just simplified into an exclusive OR gate. Yeah. All right, we might resume anyway. I think we're close to 5 minutes. The world is not just composed of D-type flip-flops. In FPGAs, we only use D-type latches and flip-flops, but we can create any other type of flip-flop that is in common use as well. One of the other flip-flops that is commonly seen is a so-called toggle or T-type flip-flop. This flip-flop has the following characteristic table. When the T input is 0, the present state is maintained. And when the T input is 1, on the next clock edge, the output of the flip-flop changes to the complement of the current state. How does that work? Well, it works by virtue of the circuitry that we have outside of the D-type flip-flop, as illustrated here. So when T is 0, then this AND gate down here is obviously going to not be active, but this upper AND gate is going to be active. And this AND gate is taking, well, the current Q value and sending it back into D. And therefore, the current state is preserved when T is 0. On the other hand, when T becomes 1, then the upper AND gate is disabled because the inverter here ensures that this input would be 0 to it. But with T being 1, this AND gate then takes the complement of the current state, namely Q bar, and feeds that through to D, the D input. And as a consequence, we have that when T is asserted, the next state of the flip-flop is the complement of its current state. Another way of expressing this equation is, as is illustrated here, the AND gates together with T, we can see that the D input is just T and not Q via that AND gate here, or it's not T and Q via this AND gate here. And therefore, this is just the exclusive OR relationship between T and the current state Q. Obviously, I hope it's obvious that the timing diagram here, whenever T is high, we see that there's a change in state of Q when the clock goes high. Here's an active clock edge, but T is low, so no change in Q. Active clock edge, T is high, therefore we get a change in Q. Active clock edge, T is high, so we get a change in Q again. A JK flip-flop is also one that has commonly been used in designs. It's sort of nice because it combines the characteristics of a number of different flip-flops, combines the features of an SR flip-flop and a toggle flip-flop via these two inputs, J and K, right? Here's the characteristic table, and I'll run you through how that emerges very quickly. So when both J and K are 0 here, obviously this AND gate is inactive, but with K being 0, this AND gate is active, and K takes the current state and feeds it back into D. So when both J and K are 0, we're just preserving the current state. When J is 0 and K is 1, then neither of these AND gates are active, and therefore D is 0, and the next state is going to be 0. If J is 1 and K is 0, then we have, as output from this AND gate, with J being 1, we have Q bar, and with K being 0, we have as the output of this AND gate Q, so we have Q or Q bar, which of course is 1. And therefore, we'll have a 1 being forced onto the output of this flip-flop. Same as S being asserted in the SR flip-flop. When both J and K are 1, well, the top AND gate is going to ensure that Q bar is provided to D, but given that K is high, this lower AND gate is D asserted, so we've got Q bar coming into D, and so the next state is going to be Q bar. All right, so we use these flip-flops in a number of other commonly occurring designs. One is a counter. We often have designs where we need to count either binary numbers or decimal numbers for whatever reason we want to count. One potential design for a counter is illustrated here. We have here 3 toggle flip-flops. The least significant one is seen over here on the left. It's got the output Q0. The middle one has the output Q1, and the one on the left has the output Q2. So it's the most significant bit. The reason they're wired up this way is because in a binary counter, we know that the least significant bit is toggling between 0 and 1 every clock cycle, right? The next more significant bit is toggling after every 2 clock cycles, or effectively, once the least significant bit has toggled, then the next more significant bit toggles. So when we see a positive going edge on Q bar, that is when the least significant bit goes back to 0, then we get a clock edge on this toggle flip-flop and causes it to go from 0 to 1. And by a similar argument, we see when this middle flip-flop goes from 1 back to 0, this Q bar will go from 0 to 1, and therefore will lead the most significant flip-flop to toggle. The only problem with this design is that we have the clock to Q propagation delay to contend with, and that this introduces a lag in each successive stage as we go to the right in this particular design. And so that we see, for example, on this rising clock edge in the middle here, where the current state of the counter is 3 and we want to go to 4, that what actually will happen as a consequence of this dependence between less significant stages switching and more significant stages switching is that we're actually going to go through a series of values before we get to the final value. We will go from from 0, 1, 1, this is the most significant bit, 0, 1, 1. This guy will go to 0 first, so we'll go from 0, 1, 1 to 0, 1, 0. Then this guy will change, so we'll go to 0, 0, 0, and then finally we'll go to 1, 0, 0. All in a very short period of time. So there's a bit of glitching that goes on there, rather than it being a smooth transition and an instantaneous transition from 0, 1, 1 to 1, 0, 0, which is what's desired. Okay? So in order to build a synchronous design, one in which the output of the counter is synchronized on the clock edge rather than on prior, less significant stages, we have to look at when do these cues or these stages of flip-flops change. So if we count up from 0 to 7, as is done in this counter, we see that Q1 changes from 0 to 1 here, and from 1 to 0 here, and from 0 to 1 here, whenever Q0 is asserted. So if we used Q0 as the T1 input, when we get an active clock edge, that would mean that we would change state. So the Q0 being 1, being an active T1 input, forces a change here from 1 to 0. Similarly, the change from 0 to 1 in the most significant bit and from 1 to 0 back again only occurs when both less significant bits are 1 in the previous clock cycle. And so we can drive the T inputs with the Q outputs rather than use the Q outputs as the clock signals for our counter. So what we should do to build a synchronous counter is to build it in this way, where the one clock signal drives all of the T flip-flops, and it's the Q signals that are telling us when should a T signal be driven here, albeit that the most significant bit is going to have to look at the Qs of all the less significant bits before it knows that the T is asserted here. Okay? So what we actually have to be a little bit careful of in this design is that we don't clock it so quickly that we don't give time for the changes in all of the Qs, the intervening Qs, to be ANDed together in order for the most significant bit to satisfy the setup time and be able to read T reliably. So we have to make sure that the clock period of this design is greater than the clock to Q propagation delay of the least significant flip-flop as well as the delay of the AND gates that we see here, plus the setup time on the most significant flip-flop. Okay, so that's a limit on how quickly we can drive this counter. Is there any question on that? Does that make sense? Okay. You have to ask if this isn't making sense to you. So we might want to control when the counter counts up. In that case, we would add an enable signal rather than driving it always with a 1. We would drive it with an enable signal. When the enable is asserted and an active clock edge comes along, then this counter is going to count up by 1. Similarly, we might at some stage want to be able to clear the counter, and we could do that asynchronously by clearing each of those D-type flip-flops that are contained within the T flip-flops, right? So structurally, we might think of the T-type flip-flop as just being a D-type flip-flop with an exclusive OR gate, and then the design of this synchronous counter with an enable is fairly systematic, and you should be able to see then that the structure is pretty easy to describe. Each stage is the same. It has an enable coming in from the AND gate. It has a clock coming in. It has the output for that stage, plus the carry to the next stage, which is really the enable being forwarded to the next stage. So all we really need to do is repeat that design as many, for the number of bits that we have in our counter. Here's a behavioral description, though, of exactly the same counter. So this is for a 4-bit up counter with an enable and an asynchronous clear. So we have the clock input, reset signal, active low with the N there, E for enable, and the output Q, which is a 4-bit value. The behavioral design is here. It consists of one process and one assignment of count to Q. Note we declare an internal signal, which is 4 bits large, called count. It's of type standard logic vector. And inside the process, we're going to be adding 1 to the count. Therefore, we have to include the unsigned package up the top here. But inside this process, it should be reasonably straightforward to see that we have an asynchronous reset for the count to make that 0 if the reset is asserted, if it goes low. Otherwise, on a rising clock edge, if the counter is enabled, increment the counter. Otherwise, the counter stays the same. Okay? And finally, we assign that count value to Q. Okay, so there's a few subtle things here that you may not immediately realize, but overall this is a reasonably clear description of how the counter works. But I did mention we've got to include this additional package so that we can do this +1 down here. If we don't include that, we can't behaviorally add 1 to a signal value, right? Q, which is an output, can't appear on the right-hand side of an assignment statement because it's an output. And therefore, we have to declare an internal signal called count that can be incremented. And finally, we make this reassignment of count back to Q. So that's only done at the end. Alternatively, we could have declared Q with mode what? Rather than declare it with mode out, we could have declared it with mode buffer. And in that way, we could have then said Q is assigned Q+1. That would have been perfectly legitimate, and we wouldn't have needed this internal signal called count. Okay? So that's an alternative. We don't actually need this final assignment here because we have an implied memory there, but it makes it a little clearer, so it's included as a nicety. Is this code clear? In that case, what are the advantages of the behavioral code over the structural code for this design? The structural code would replicate this component 4 times and wire it up properly, right? And unless I called the component counter, would you have any idea what it's doing? Here it's clear what the counter is doing. Do you have any idea how it's implemented? You leave it up to the compiler, right? So which is better, the structural or the behavioral description? Yeah.
Depends on who's reading it after. And how much time you
What would you prefer?
Well, I would rather do this because I would want to
Who do you think would prefer the structural version?
have to optimize the designs very intensely.
How could you optimize it further?
I'm not sure.
No, neither am I. Look, I think for 99% of readers, the behavioral version is going to be desirable, better, easier to maintain, easier to understand what it's doing. So I think this is preferred. This is a reasonable example of why you might need a process, right? Not a mux. Okay. Now, you won't necessarily always want to start a counter from 0. This design with a mux in front of the exclusive OR gate allows us to load a value, the D values in here, in parallel when the load signal is asserted, or when load is not asserted, but enable is asserted, allows us to count up from whatever the current value is. Okay, so we can load whatever value, whatever 4-bit value we wish into this counter. It doesn't have to be 0. Okay, so this is that design, synchronous load, synchronous enable, and asynchronous reset. So here's the asynchronous reset. This time we have declared Q as a buffer type signal, but the signal is of type integer, right? In this case, we need to specify what range we want that integer to work over. Otherwise, the synthesis tool doesn't know how many bits to assign to that integer. We have, but because it's integers, we don't really need the unsigned, the standard logic unsigned, the IEEE standard logic unsigned package, because the integers are an inbuilt type. VHDL knows how to add 1 to an integer, okay? Why do we need standard logic 1164 up here? Because we have standard logic signals. Clock, reset, load, and enable, right? So on an active clock edge, if load is 1, then we're going to assign to Q D. So we're going to load D into Q. D is an input here. Otherwise, if the enable is 1, we're going to add 1 to Q. Otherwise, Q is just going to stay at whatever value it had, right? Because there's no default assignment to Q here. Here's a design for a counter that can count up to 5 and then it clears itself. Why? Because when we get to 5, this AND gate is asserted and asserts the load signal, and the value that gets loaded is 0. So we see this counter counting from 1, 2, 3, 4, 5, then back to 0. It's a synchronous load. Similar approach is used to build a 2-digit BCD counter. So at the top here we have the less significant BCD digit. When it gets to 9, see we're tapping Q3 and Q0, this AND gate asserts, and therefore the load signal is going to be asserted, and we're going to get 0 loaded back into here. So that top guy is going to count from 0 to 1, up all the way up to 9, and then go back to 0 again, right? When we get to 9 at the top, though, we also have an enable signal for the more significant BCD counter down here. So every time we get to 9, the enable signal is asserted. So on the next active clock edge, this guy's going to count up by 1 from wherever it was. And when this guy gets to 9, this AND gate is asserted only when the when the less significant BCD digit is 9 as well. That's why we have 3 inputs to this AND gate. And that's when the more significant counter is going to go back to 0. Okay? We can also clear the counter to 0 by asserting this clear signal here. So it's a really neat little design for a stopwatch, let's say, which is counting hundredths of seconds, assuming that the clock here were set to be 100 hertz. This is an example of a modulo 6 counter, but using an asynchronous clear. When this guy gets to 5, this NAND gate goes low, and as a consequence, the clear inputs on these toggle flip-flops is asserted. The problem with this is the design gets to 5, and the NAND gate then goes low at 5 and immediately asynchronously clears these T-type flip-flops. So we go to 0 from 5 very quickly. So it doesn't stay at that value 5 for very long, and that could be completely misinterpreted by any downstream, any user circuit, any circuit that uses this counter and relies on it to be a modulo 6 counter. It's not going to see this 5 for a whole clock period. It's only going to see it for a very short, brief amount of time. So that's not very desirable. All right. Look, I think I've worn out your welcome. We might leave it here and pick up here on Tuesday. And call it a day. Are there any questions on what I've talked about? No? All right. Have a good weekend. Don't go too wild tonight. And don't forget that there's a lab due on Sunday night, midnight, unfortunately. All right. So the problem is that previously we argued that when the clock goes high, the fact that P2 goes to 0 prevents any further changes on D from getting into the flip-flop, because the 0 at this point means that this NAND gate has a 0 input, and therefore its output must go to 1, and it stays at 1 for the period that P2 is 0. Do you remember that? Because you've got to understand that before we talk about anything else. If this point, P2, goes to 0, right? If this guy goes to 0, then that means that this input to this NAND gate is 0, and as a consequence, the output of that NAND gate must be 1. So it doesn't matter what D changes to, P4 stays at 1. while P2 is 0,
Yes.
the output of this NAND gate P4 is always 1. Doesn't care what, doesn't see D.
As soon as it becomes
So
programmed.
what is TH?
I'm coming to that. I want you to
It's just like odd.
accept that that's what's happening. Do you understand that?
Little circle.
That if P2 is 0,
This is-
P4 is 1.
I'm exploring 3 additional
Yeah?
processes in the concurrent thread.
Now, the problem is that it takes time from the clock to go, from between the clock going high and P2 goes to 0.
See, why is
Takes delta
concurrency
time.
here okay, but in C it's like a no.
If D changes immediately after the clock changes, it's possible for P4 to change before P2 goes to 0.
Quite the same value, that will stay like
So it's like stuff like this with like the timing diagram.
Because if P2 is still 1,
there's
if
something
D
like,
changes,
there's something
you will
like
see
levels
not
that's
D come out of
being
P4.
restrained by this stuff. Because like surely.
And if that happens to be a 1 rather than a 0, then that means the state of the whole flip-flop is now undecided. Now it doesn't know, should it change to a 1 or should it change to a 0?
I think it gets close.
Yeah,
So
yeah.
And then this is over.
The problem is that
Yeah, right.
And so like somehow it sorts
if
out.
this changes at a time very close to this changing, then it's possible that our assumption that P2 being at 0 prevents any further changes on P4
It still knows the value.
while the clock is high
And it's
is
like one of the
invalid.
values-
It's no longer the case.
Like, you know how C diagrams come from.
Because there's a window of time between clock going to 1 and this going to 0, during which any change in D is going to actually impact on P4. And as a consequence of that, it's possible for all of the D values here, D and D bar, to change again.
But like the things like clocks and stuff, like we've seen that it's not fine sometimes, and you can end up with like clock
So
setting.
Yeah.
D should keep stable to wait.
So it feels like there's a lot of
T2
complexity.
To go to 0.
The fact that we
Indeed.
deal with simple stuff and
Yeah.
this is still
Indeed.
Yeah.
that would be like
TH
shielded
is
stuff.
just
I think
one
this is
delta.
this tool is so big because people were saying like
Not necessarily.
in the lab, people were saying
The
like,
delta
you
that
just
you
wrote, like,
see on
slam
this
and use
gate
OHDL
is bigger than the
from
delta
scratch.
that you see on this gate.
So they fixed that.
This
They
has
made it so
3
it's much more
inputs
coded
and this
now,
has
so
2
they
inputs.
tried
This
to,
is going to
like,
be a
fix all
faster
the
gate than
things
that
They
gate.
worded it to being like 100 megabytes something.
Okay.
But
So we have to wait for, yes, we have to wait for this gate to change. And ideally, we have to wait also for the delay on this gate before we change D. Because we want that 0 here to impact P4. We want the 0 here to become a 1 out here before we change D.
like the generate stuff, that's not usually complicated to write. It's the it's the complicated, like it's this behavioral process stuff where you have
It
something
is-
that looks at this.
You
and
definitely don't want to
it's a certain
change
diagram that can
D
do a certain-
until P2 is 0. Definitely not.
You know, an 8.
Because if it changes before that, it's
Yeah, but writing
possible
the synthesis
this
code that can
NAND
read
gate
this
will
and know
switch
what to do with it.
from
That's-
1
I know
to
how
0.
to do that.
But it'd be so much slower, because you look at that, it's just
So
8-bit
so
record.
TH is
How big of it is it? It's just like,
equal.
I'm not saying that it's equal to delta. I'm just giving you an argument as to why
16.
there is a period of time that you have to wait
And then you've got
after the clock goes high before you're allowed to change D safely. If you change it before that period of time, which, yes, looks like delta from this analysis, if you change it before that time, it can impact on the output of the flip-flop.
So why is not equal to delta? We just need
I don't know what other parameters you have to... This is a bit of a hand-wavy argument as to how much time you have to present an input before that gate actually will reliably switch.
It's like just this one vote kid.
So this input we know won't change until, well, probably a little bit after delta because there's still a propagation delay on the wire as well. But apart from that, it depends on the momentum in this gate. It depends on the resistance, the capacitance of this gate, as to how long it will take to change once P2 goes to 0 and if D were to change. And that may also be asymmetric. We're using very, very broad generalizations to say all gates change at delta time. The minutiae are a lot more varied. There's many differences, many factors that come into play. Roughly speaking, to a very coarse analysis, yes, you should not change D until at least delta time after the clock changes.
I see. Thank you.
So I'm not asking you to reproduce or to explain how large TH is. I want you to understand what the reasons for it are, why that comes about.
Yes.
Hmm.
Small question. Do we need to understand every circus here?
I think you should understand those circuits, but we haven't got to those
Yes.
slides yet.
Okay, thank you.
Yeah, the circuits, like, once I've presented them, it should be clear to you how the circuit works.
Yes. Thank you.
No worries.
Afternoon.
Hey.
I was just wanted to ask or inquire about the Engineers Australia panel, because I'm Aidan. by the
Oh,
way.
right. Oh, so you're Aidan.
I am
okay.
Aidan, yes.
Pleased to meet you.
Pleased to meet you.
Okay. Aidan Manning.
Yes, that
Right.
is me.
Good. So what did you want to know?
I guess just how the panel works. Like,
I've never been in one,
You've never
so
been
I
in
don't
one.
really know. In principle, what they're going to be doing is they want to find out, what your experiences of the degree have been.
okay.
You won't be interviewed on your own. It's not a one-on-one
Sounds like a
interview. There'll be a panel of interviewees.
Yep.
Interviewers. And there'll be about 30 students in the room, because it's not just CompEng, it's also SEng and bioinformatics students that are going to be in the room.
Okay.
It's going to be about 10 across all second, third and fourth year.
Okay.
And broadly speaking, we want a mix that represents the student body. So
it's like a forum than an interview.
It is,
Okay.
but the interviewers will ask questions, and it'll be to the whole room,
Okay.
and it'll be up to individuals, I guess, who
put their hand
feel
up.
like they have something to say
Yeah.
that would respond.
Yep. Oh yeah, well, I'll do
Yeah,
that.
that's the whole idea.
I'd love to do
So
that.
thank you very much. Would you please
I'll
email
email,
me,
yeah.
just so that I've got that down?
Yeah.
There will be more contact eventually about it.
That's
Yeah, oh, that's great. Okay, one more.
Have you been having a hard time?
No, not really, because we're really just, it's early days. The interviews in June, or the panels are in June, so there's still plenty of time, but I wanted to get my participants sorted rather than not.
Then
Yeah.
have to do it last minute.
That's right. Who knows whether I'd succeed at the last moment. So
Is
it's
this
better
a
to...
computer engineering specific thing? Or?
No, it's for all engineering degrees, actually, all engineering specializations. So all 21 or 22 of them are going to be assessed, accredited. Sorry?
Oh, this is.
They're all being accredited. Chemical engineering, mechanical,
so
all
this
of them.
is Engineers Australia
Yeah.
coming in and being like, we're
Yeah.
just going to check and make sure your engineering
Yeah.
degree is still,
That's right.
still legit. Okay.
Every 5 years, we need to be re-accredited.
Oh, that's cool.
No, it's not. It's a huge
Okay.
amount of work for very little benefit. Okay,
Yeah,
the
I
benefit
imagine
is
very few-
you guys graduate and are professional engineers.
It's more philosophy for you.
We have to put together a massive report.
Yeah.
Effectively, every degree program, so every specialisation has had to prepare a very large report. The CSE one's about 150 pages, and that's only one. There's several reports that go into it. essentially describing our degrees and how we assess and how we assure that the graduate qualities, graduate capabilities are met, and they're interested in how much professional exposure you get, how much teamwork you do,